Neptune's extreme distance meant light levels were 400 times dimmer than Earth experiences. Voyager's cameras required long exposures, risking blur from the spacecraft's motion. Engineers developed sophisticated image processing techniques to compensate, allowing Voyager to capture stunning images of this distant world. Voyager 2 revealed Neptune's dynamic atmosphere, discovered the Great Dark Spot, measured the planet's rapid rotation and powerful winds, detected separate cloud decks that emerged and dissolved within hours, and found that giant storms circled the entire planet in 16 to 18 hours. The spacecraft flew past Triton, discovered its geysers, and measured its frigid surface temperature. Voyager detected Neptune's rings, confirmed their arc structures, and measured the planet's unusual magnetic field. Then Voyager 2 departed, heading into interstellar space. No spacecraft has visited Neptune since. Everything we've learned about Neptune in the past 36 years comes from Earth-based telescopes and space observatories like Hubble and now James Webb. These distant observations have revealed much: the atmospheric temperature changes, the reversing storms, the fading ring arcs, the auroral conformation. But they can't answer Neptune's deepest questions. We need answers that only a dedicated Neptune mission can provide. Why does Neptune's thermosphere burn at 750 Kelvin when it should be frozen? The planet sits 30 times farther from the Sun than Earth. Ultraviolet radiation can't explain temperatures reaching 477 degrees Celsius in the upper atmosphere. Some scientists suggest atmospheric interaction with ions in Neptune's magnetic field generates this heat. Others propose gravity waves from the interior dissipate energy as they reach higher altitudes. But we're essentially guessing. Without direct measurements from an orbiter equipped with specialized instruments, we're trying to solve a puzzle with most pieces missing. Neptune's internal heat generation poses equally baffling questions. The planet radiates approximately 3 times more energy than it receives from the Sun. This internal heat drives Neptune's violent weather despite receiving only 1,000th the solar energy Earth enjoys. Temperatures at Neptune's core reach approximately 5,400 Kelvin, hot enough to vaporize rock. But what generates this heat billions of years after the planet's formation? Gravitational contraction? Radioactive decay? Some exotic process we haven't imagined? Jupiter and Saturn generate internal heat through gravitational compression as they slowly contract. Does Neptune employ the same mechanism, or does something else occur within its mysterious interior? The formation of Neptune itself remains contentious. Traditional planetary formation models struggle with ice giants. These models work reasonably well for terrestrial planets and gas giants. But Neptune and Uranus occupy an uncomfortable middle ground. Core accretion theory suggests planets form when solid material gradually accumulates, eventually capturing surrounding gas if the core grows massive enough quickly enough. The problem? Neptune formed in a region where material was sparse and orbital periods were long. Calculations indicate Neptune should have taken longer to form than the solar nebula existed. Either Neptune formed much closer to the Sun and migrated outward, disrupting the entire early solar system in the process, or our formation models need fundamental revision. Recent discoveries make this ice giant problem more urgent. Exoplanet surveys reveal that Neptune mass planets are among the most common types of worlds in the galaxy. Understanding how Neptune formed isn't just about our solar system anymore. It's about comprehending planetary system evolution throughout the universe. If we can't explain Neptune's existence, we can't fully understand the thousands of similar worlds astronomers discover around other stars. December 2025 brought Neptune's most startling revelation yet. New hybrid modeling suggests Neptune might not be the icy world we've imagined for decades. The classification ice giant implies a planet dominated by water, methane, and ammonia ices surrounding a small rocky core. But recent analysis indicates Neptune could just as easily be rock-dominated, with rock-to-water mass ratios potentially ranging from 0.20 to 1.78. This isn't a minor refinement. This fundamentally challenges what Neptune actually is. The uncertainty stems from our observational limitations. We've never sent a probe into Neptune's interior. Everything we know comes from gravitational measurements, magnetic field observations, and theoretical modeling. Those observations can support multiple internal configurations. Neptune might contain a relatively small rocky core surrounded by thick layers of exotic ices, or it might possess a massive rocky interior extending halfway to the surface, with only thin ice layers above. Both scenarios match available data. If Neptune is more rock than ice, planetary formation theories face major revision. Rock-dominated Neptune would require different formation conditions, different migration histories, different evolutionary pathways than ice-dominated Neptune. It would mean astronomers have fundamentally misunderstood one of our solar system's major planets for the entire history of modern astronomy. The implications extend to every Neptune-mass exoplanet discovered. Are they ice giants, rock giants, or something between? Computer simulations from recent years suggest Neptune's interior might be even stranger than previously imagined. Models indicate that under the extreme temperatures and pressures inside Neptune, mixtures of water, methane, and ammonia would naturally separate into distinct immiscible layers, like oil and water refusing to mix. Hydrogen would be squeezed out of methane and ammonia molecules that dominate the deep interior, creating a layered structure resembling a cosmic cocktail with components that refuse to blend. This stratification could explain Neptune's bizarre magnetic field. Earth's magnetic field originates from convection in a liquid iron core, a relatively simple dynamo. Neptune's field doesn't work that way. The dramatic tilt and offset suggests the field originates not from a core dynamo, but from thin shells of conducting material in the upper mantle. If Neptune's interior is stratified into immiscible layers, convection would occur differently, generating magnetic fields through mechanisms unlike anything seen on Earth, Jupiter, or Saturn. Neptune and Uranus might represent an entirely different category of magnetic world. Researchers have even identified a candidate molecule that might explain these unusual fields, aquodium, an exotic substance that cannot form under Earth conditions, might exist within Neptune's high-pressure interior. This molecule could create the conducting layers that generate Neptune's offset, tilted magnetic field. But proving aquodium exists requires direct sampling or detailed spectroscopic analysis from a dedicated mission. From Earth, we're simply too far away to confirm such exotic chemistry. The mystery extends to Neptune's atmosphere. Between 2003 and 2018, globally average temperatures in Neptune's stratosphere dropped by roughly 8 degrees Celsius. This cooling was completely unexpected. Neptune experiences seasons like Earth: summer, winter, spring, and fall. But each Neptunian season lasts over 40 Earth years because Neptune requires 165 years to complete one orbit. During the observation period, Neptune's southern hemisphere was experiencing early summer. Temperatures should have been gradually warming, not cooling dramatically. Then everything reversed. Observations from 2018 to 2020 showed Neptune's south pole warming by roughly 11 degrees Celsius, completely reversing the previous cooling trend. Such rapid polar warming had never been observed on Neptune before. The cause remains unknown. Scientists have proposed several theories. Changes in atmospheric chemistry might alter how effectively the upper atmosphere radiates heat into space. Random weather pattern variability could drive temperature fluctuations. Neptune's atmosphere might respond to the 11-year solar activity cycle, though this seems unlikely, given that Neptune receives only 0.1% of the sunlight Earth enjoys. The solar connection intrigues researchers specifically because it seems impossible. How could a world so distant respond to solar variations, yet correlations appear in the data? When solar activity increases, Neptune's atmosphere seems to warm. When solar activity declines, cooling follows. The mechanism remains mysterious. Perhaps solar wind variations affect Neptune's magnetosphere, which influences upper atmospheric heating. Perhaps cosmic ray flux modulated by solar activity affects cloud formation, altering Neptune's energy balance. Or perhaps we're seeing coincidental correlations in limited data. These temperature mysteries connect to Neptune's storm behavior. Hubble observations revealed something unprecedented in 2018. A massive dark vortex appeared in Neptune's northern hemisphere, an anticyclonic storm similar to Jupiter's Great Red Spot. Over the following year, this storm drifted southward toward the equator. Atmospheric models predicted the vortex would dissipate once it reached equatorial latitudes, torn apart by wind shear and lacking the Coriolis forces that sustain such storms at higher latitudes. But the storm didn't die. In August 2020, the vortex abruptly changed direction, doubling back northward. This represented the first time scientists had observed a Neptunian storm reverse course. Hubble also spotted a smaller dark spot that temporarily appeared near the larger vortex. This smaller feature might have been a piece of the giant storm that broke off, drifted independently, then disappeared. Computer simulations had predicted such fragmentation, but nobody had ever witnessed it actually happening. Dark spots present another Neptune enigma. These massive storms appear preceded by increased cloud activity 2 to 3 years before the vortex becomes visible. The storms exist for only a few years before disappearing. The Great Dark Spot Voyager, two discovered in 1989, had completely vanished by the time Hubble observed Neptune in 1994. New dark spots appear and disappear on irregular schedules. Their formation mechanisms, energy sources, and destruction processes remain poorly understood. The disappearance mechanism might involve companion clouds. High-altitude methane ice clouds often form above dark vortices. These bright companion clouds make the dark spots visible by providing contrast. Some researchers suggest these companion clouds eventually reach the storm's center, blocking the blue wavelengths astronomers use to track the vortex. The storm might still exist, just invisible beneath its cloud cover. Or the companion clouds might somehow disrupt the vortex itself, causing genuine dissipation. Neptune's ring system adds yet another layer of mystery. The Adam's ring contains 5 distinct arcs rather than forming a continuous band. These arcs, named Liberté, Égalité 1, Égalité 2, Fraternité, and Courage, occupy a narrow range of orbital longitudes and have remained remarkably stable since their discovery in 1984. This stability shouldn't exist. Differential orbital motion should cause ring arcs to spread uniformly around Neptune within just a few months. Material in slightly lower orbits moves faster than material in higher orbits, creating shearing forces that should distribute particles evenly. Yet Neptune's ring arcs persist for decades. The leading arcs, Courage and Liberté, have faded recently, but the trailing arcs, Fraternité and Égalité, remain stable and persistent. The stability probably relates to resonant interactions between the Adam's ring and Galatea, Neptune's inner shepherd moon. Galatea's gravity might create zones where ring particles accumulate, maintaining the arc structure against differential shear. But the detailed physics remains unclear, and the recent fading of some arcs while others persist only deepens the puzzle. Neptune's rings contain extremely dark material, likely organic compounds processed by radiation, similar to materials in Uranus's rings. The proportion of dust ranges between 20% and 70%, unusually high compared to Saturn's primarily icy rings. This dust gives Neptune's rings very low optical depth, making them difficult to observe and study from Earth. Even the brightest sections of the Adam's ring reflect less than 0.1% of incident sunlight. All these mysteries, the bizarre magnetic field, the impossible ring arcs, the reversing storms, the unexplained temperature variations, the uncertain interior composition, share a common theme. We're trying to understand Neptune from 4 billion kilometers away, using instruments designed for other purposes. Hubble wasn't built specifically for Neptune. James Webb observes primarily in infrared wavelengths optimized for distant galaxies, not planetary atmospheres. Ground-based telescopes peer through Earth's turbulent atmosphere, blurring fine details. What we need is a dedicated Neptune mission, a spacecraft designed specifically to answer Neptune's deepest questions, an orbiter that could spend years studying the planet's atmosphere, tracking storms through complete seasonal cycles, mapping temperature variations across latitudes and altitudes, measuring atmospheric composition and dynamics with dedicated instruments, probes that could descend into Neptune's atmosphere, directly sampling composition, pressure, and temperature profiles, penetrators that could study Neptune's interior structure, magnetic field generation mechanisms, and internal heat sources. Multiple mission proposals exist. NASA's Ice Giants Predecadal Survey Mission Study examined potential Neptune orbiter concepts. The European Space Agency has considered Neptune missions as part of their long-term planning. Chinese Space Agency documents mention outer solar system exploration. Independent academic groups have designed mission architectures, calculated trajectories, and identified key science objectives. But as of 2026, no Neptune mission has received funding or approval. The challenges are formidable. Neptune lies 30 times farther from the Sun than Earth. Solar panels become nearly useless at such distances, requiring nuclear power systems. Travel time exceeds 12 years, even with gravitational assists. Communications suffer from 40-minute light travel delays. Mission costs reach billions of dollars. Competing priorities for Mars, Europa, and near-Earth missions consume available budgets. Yet one critical factor works in Neptune's favor. Triton, Neptune's largest moon, represents one of the most compelling science targets in the outer solar system. Triton orbits Neptune retrograde, revolving opposite to the planet's rotation. This backward motion marks Triton as a captured object, a Kuiper Belt dwarf planet, that Neptune's gravity ceased billions of years ago. That capture event would have been catastrophic. Gravitational interactions scattered or destroyed any pre-existing Neptunian satellites. Triton's orbit circularized over millions of years through tidal heating, melting and reshaping its interior. The moon we see today bears the scars of this violent history. Voyager 2 found Triton's surface, temperatures reaching negative 391 degrees Fahrenheit, one of the coldest objects ever measured in the solar system. Yet Triton displays remarkable geological activity. Active geysers erupt through its icy crust, driven by sublimating nitrogen ice heated by faint sunlight. These geysers make Triton one of only a few geologically active moons in our solar system. The combination of extreme cold and active geology creates a unique environment. Triton's surface shows evidence of past liquid water, cryovolcanism, and ongoing resurfacing. Its thin nitrogen atmosphere, constantly renewed by sublimation, creates seasonal changes despite the moon's incredible distance from the sun. Tidal interactions cause Triton's orbit to gradually decay. The moon spirals closer to Neptune by about 4 centimeters per year. In 3.6 billion years, Triton will pass within Neptune's Roche limit, the distance where tidal forces exceed the moon's structural strength. The result will be either collision with Neptune's atmosphere or Triton's breakup, forming a massive ring system potentially more spectacular than Saturn's. A mission to Neptune becomes a mission to Triton by default. Any spacecraft orbiting Neptune could study Triton extensively through repeated flybys. The moon's retrograde orbit simplifies trajectory planning. Its geological activity offers insights into cryovolcanism, tidal heating, and atmospheric dynamics at extreme temperatures. Triton might harbor a subsurface ocean beneath its icy shell. Tidal heating from orbital decay could maintain liquid water layers similar to those suspected beneath Jupiter's moon Europa or Saturn's moon Enceladus. If such an ocean exists, it could potentially support microbial life, making Triton an astrobiology target comparable to the more famous ocean worlds. This dual science return, Neptune itself plus Triton, strengthens mission proposals considerably. You're not just studying one enigmatic ice giant. You're studying a captured Kuiper Belt object, an active cryogenic world, and potentially an ocean moon. 3 major science objectives in one mission architecture. The Voyager 2 flyby demonstrated what's possible with dedicated instruments. On August 25, 1989, Voyager 2 made its closest approach to Neptune, culminating the grand tour of the solar system's 4 giant planets. The encounter was technically challenging due to Neptune's extreme distance and resulting low light levels. Voyager 2's cameras captured images of Neptune's dynamic atmosphere, despite receiving only 3% of the sunlight available at Jupiter. The spacecraft discovered separate cloud decks, cloud systems emerging and dissolving within hours, and giant storms circling the planet within 16 to 18 hours in the upper layers. The mission revealed Neptune's winds, the strongest sustained winds in the solar system, reaching 2,100 kilometers per hour, 3 times stronger than Jupiter's, 9 times stronger than Earth's most powerful hurricanes. This despite Neptune receiving so little solar energy. Voyager 2 discovered the Great Dark Spot, an anticyclonic storm comparable to Jupiter's Great Red Spot. The spacecraft observed Neptune's ring system in detail for the first time, revealing the unexpected ring arcs. It detected Neptune's bizarre magnetic field and measured the planet's internal heat output. The Triton flyby provided equally stunning results. Voyager 2 captured images of the moon's cantaloupe terrain, cryovolcanic features, and active nitrogen geysers. It measured surface composition, atmospheric properties, and geological activity that shouldn't exist on such a cold world. All this from a single flyby, lasting just hours. Imagine what an orbiter could accomplish across years of dedicated observations. Modern mission concepts build on Voyager's foundation while incorporating technologies unavailable in the 1970s. Advanced cameras and spectrometers could map Neptune's atmosphere in wavelengths from ultraviolet through infrared, tracking storms through complete seasonal cycles, measuring atmospheric composition and dynamics with unprecedented precision. Dedicated magnetometers could map Neptune's magnetic field structure in 3 dimensions, determining how the field is generated and why it exhibits such extreme tilt and offset. Plasma instruments could study the interaction between Neptune's magnetosphere and the solar wind, measuring particle populations and energy flows. Atmospheric probes could descend into Neptune's clouds, directly sampling composition, pressure, and temperature profiles at different altitudes and latitudes. They could measure wind speeds at various depths, test predictions about atmospheric chemistry, and search for the transition zones where hydrogen and methane separate into layers. Radar instruments could peer through Neptune's clouds, studying deeper atmospheric layers and potentially even probing the planet's interior structure. Penetrating radar has revolutionized our understanding of Mars, Titan, and Venus. Similar technology could finally answer questions about Neptune's internal composition. Triton would receive comparable attention. High-resolution imaging could map the Moon's entire surface at scales revealing geological processes in detail. Thermal mapping could identify active regions where subsurface heat reaches the surface. Spectroscopic observations could determine surface composition and search for signs of subsurface water. A Triton lander represents a more ambitious but scientifically compelling option. Landing on Triton would be technically easier than landing on Europa or Enceladus due to lower gravity and the absence of intense radiation. A lander could study surface composition directly, measure seismic activity, analyze atmospheric properties, and potentially even detect subsurface ocean signatures through magnetic induction measurements. Several specific mission proposals have progressed beyond initial concepts. NASA's Ice Giants pre-decadal survey examined Neptune orbiter architectures in detail. One concept featured a main orbiter studying Neptune, plus a Triton lander deployed after Neptune orbit insertion. Launch windows occur approximately every 13 years, with the next optimal opportunity in the early 2030s. The European Space Agency has considered Neptune missions as part of their Voyager 2050 long-term planning framework. ESA concepts emphasize international collaboration, potentially partnering with NASA or other space agencies to share costs and technical expertise. European contributions might include specific instruments, atmospheric probes, or mission components leveraging ESA's experience with Rosetta, Huygens, and other planetary missions. Chinese Space Agency documents mention outer solar system exploration as part of long-term objectives. China's successful Mars and lunar missions demonstrate growing technical capabilities. A Neptune mission could represent a flagship achievement, showcasing Chinese space technology while contributing valuable science data to the international community. Independent academic groups continue designing mission concepts and advocating for ice giant exploration. These studies identify key science questions, design instrument packages, calculate trajectories, and estimate costs. While lacking official funding, academic mission designs often influence later formal proposals by demonstrating technical feasibility and scientific value. The technical challenges remain formidable, but not insurmountable. Solar panels become nearly useless at Neptune's distance, requiring nuclear power systems. NASA's multi-mission radioisotope. Thermoelectric generators provide reliable power regardless of distance from the Sun. These systems powered Voyager 2, Cassini, Curiosity, and Perseverance successfully. Travel time exceeds 12 years, even with gravitational assists from Venus, Earth, and Jupiter. This requires spacecraft systems robust enough to survive decades in the harsh space environment. Radiation exposure, micrometeorite impacts, thermal cycling, and component aging all threaten long-duration missions. Communications suffer from 40-minute light travel delays at Neptune's distance. Commands sent from Earth take 40 minutes to reach the spacecraft. Responses take another 40 minutes to return. This precludes real-time control during critical mission phases like orbit insertion or probe deployment. Spacecraft must execute these maneuvers autonomously, using pre-programmed sequences. The distance also reduces data transmission rates dramatically. Radio signals spread out over vast distances, arriving at Earth extremely weak. Even with large ground antennas and sensitive receivers, data rates at Neptune remain far slower than at Mars or even Saturn. High-resolution images and spectroscopic data must be transmitted gradually over days or weeks. Mission costs reach several $billion. Voyager 2 cost approximately $4 billion in today's currency. Modern missions with more sophisticated instruments, longer operational lifetimes, and additional mission elements like probes or landers would cost considerably more. NASA's proposed Neptune orbiter concepts range from $3 to $5 billion. Competing priorities consume available budgets. Mars Sample Return, Europa Clipper, Dragonfly to Titan, and various near-Earth missions all vie for the same funding. Political realities mean flagship missions require sustained commitment across multiple administrations. Budget uncertainties and changing priorities can derail missions even after approval. Despite these obstacles, the scientific case for Neptune exploration remains compelling. Neptune represents an entire class of planets, ice giants, that appears common throughout our galaxy. Exoplanet surveys reveal Neptune-mass worlds orbiting other stars frequently. Understanding ice giant formation, composition, and evolution informs our understanding of planetary systems generally. The ice giant problem, explaining how Neptune and Uranus formed, remains unsolved. Traditional core accretion models struggle with timing. Planets either grow too slowly to capture substantial nebular gas before it dissipates, ending up as small rocky worlds without hydrogen-helium envelopes, or they grow so rapidly they reach runaway gas accretion and become hydrogen-dominated gas giants like Jupiter. Forming ice giants with substantial fractions of both heavy elements and hydrogen-helium requires precise timing and fine-tuning in models. Recent theories propose Neptune and Uranus formed closer to the Sun, then migrated outward through gravitational interactions with other planets and remaining planetesimals. Testing these formation scenarios requires detailed knowledge of Neptune's interior composition and atmospheric properties. Neptune's extreme weather, despite minimal solar heating, challenges our understanding of atmospheric dynamics. Internal heat drives Neptune's storms and winds, but the mechanisms remain unclear. Studying Neptune's weather through complete seasonal cycles would reveal how internal and external energy sources interact to produce atmospheric phenomena. The bizarre magnetic field requires explanation. Recent computer simulations suggest water, methane, and ammonia separate into immiscible layers under the temperatures and pressures inside Neptune. Hydrogen gets squeezed out of methane and ammonia in the deep interior, creating stratified layers like oil and water. These immiscible layers might explain why Neptune's magnetic field differs so dramatically from Earth's, Jupiter's, and Saturn's. The field might originate from thin conducting shells in the upper mantle rather than deep core convection. This layered interior model has profound implications. If correct, it suggests Neptune's interior structure is far more complex than the simple three-layer model that dominated thinking for decades. It would explain not just the magnetic field, but also observations about Neptune's heat flow, atmospheric composition, and possibly even the diamond rain forming deep inside. Testing this model requires detailed measurements impossible from Earth. We need to map Neptune's gravitational field precisely, revealing mass distribution inside the planet. We need to measure how Neptune's magnetic field varies with location and time, constraining where and how the field is generated. We need atmospheric composition measurements at different depths, testing predictions about how materials separate under extreme conditions. Triton adds urgency to mission planning. The Moon's gradual orbital decay means its geological activity might not persist indefinitely. Studying Triton now captures a unique window when the Moon remains geologically active, maintains a thin atmosphere, and displays ongoing resurfacing. Delaying decades might mean missing Triton's active phase. The Moon's potential subsurface ocean represents another time-sensitive target. If tidal heating from orbital decay maintains liquid water beneath Triton's ice shell, that ocean might support microbial life. Studying Triton joins the search for life beyond Earth, alongside Europa, Enceladus, and Titan. These ocean worlds represent our best near-term opportunities to discover extraterrestrial biology. So Neptune waits, 4 billion kilometers away, wrapped in mysteries we've barely begun to unravel. Its bizarre magnetic field wobbles through space. Diamond rain falls through its depths. Storms reverse course for reasons unknown. Ring arcs persist against all expectations. And nearby, Triton erupts with geysers while slowly spiraling toward eventual destruction. Every mystery points toward the same conclusion. We need to go back. The scientific case grows stronger each year. NASA's Planetary Science Decadal Survey identified an ice giant mission as a priority, recognizing that Neptune and Uranus represent a major gap in our exploration of the solar system. We've sent multiple missions to Mars, several to Jupiter and Saturn, yet we've visited the ice giants only once, briefly, decades ago. That imbalance reflects outdated priorities from an era when we didn't understand how common Neptune-mass planets are throughout the galaxy. Exoplanet discoveries changed everything. Telescopes like Kepler revealed that Neptune-sized worlds are among the most abundant planets orbiting other stars. They're more common than Jupiter-sized gas giants, more common than Earth-sized terrestrial planets. Understanding how these intermediate mass planets form, evolve, and develop atmospheres suddenly became crucial for interpreting observations of thousands of exoplanets. Neptune stopped being just another solar system member and became the template for understanding the galaxy's most typical large planets. Several mission concepts have been proposed. The Trident mission would conduct a single flyby of Neptune and Triton, similar to Voyager 2, but with modern instruments. It would map Triton's surface at high resolution, measure atmospheric composition on both bodies, and study Neptune's magnetic field during the encounter. A flyby mission could be built relatively inexpensively and launched within a decade, providing quick returns on scientific investment. But flyby missions have limitations. Voyager 2 taught us that brief encounters reveal mysteries without answering them. The Great Dark Spot appeared in Voyager images, then vanished by the time Hubble looked again. Was it dissipating during Voyager's approach? Did it form shortly before the flyby? We'll never know because we only had those few hours of observation. Understanding Neptune's dynamic atmosphere requires watching storms evolve over weeks and months, tracking how they form, drift, and disappear. Orbiter missions offer that extended observation time. A Neptune orbiter could spend years studying the planet and its moons, watching complete seasonal cycles, tracking magnetic field variations, monitoring atmospheric changes. It could observe Triton repeatedly from different angles and distances, mapping the entire surface at high resolution while studying how geysers vary with orbital position and seasonal timing. An orbiter transforms brief glimpses into comprehensive understanding. The technical challenges are formidable. Neptune orbits 30 times farther from the Sun than Earth, where sunlight is 900 times dimmer. Solar panels that work perfectly near Earth generate almost no power at Neptune. Nuclear power becomes necessary. Radioisotope thermoelectric generators, which convert heat from radioactive decay into electricity, provide the only viable power source. But these systems are expensive, require rare plutonium-238, and generate limited power compared to solar panels. Communication presents another challenge. Radio signals from Neptune take over 4 hours to reach Earth, traveling at light speed across 4 billion kilometers. That 8-hour round-trip delay makes real-time control impossible. Spacecraft must operate autonomously, making decisions without waiting for instructions from mission control. They need sophisticated onboard systems capable of recognizing and responding to problems, adjusting observations based on what they find, managing power and data storage independently. Getting to Neptune takes time. Even with gravity assists from Jupiter, the journey requires 12 to 14 years. Engineers must design systems that remain functional after more than a decade in space, exposed to radiation and micrometeorite impacts. Every component must be redundant, every system robust enough to survive the long voyage. The mission profile demands patience, committing to science returns that won't arrive until the 2040s at the earliest. Cost compounds these challenges. Outer planet missions rank among the most expensive robotic spacecraft NASA builds. The Cassini mission to Saturn cost over $3 billion. A Neptune orbiter would likely cost similar amounts, competing with other scientific priorities for limited budget resources. Planetary scientists must make difficult choices, balancing the transformative science from Neptune against equally compelling targets elsewhere in the solar system. Yet the scientific payoff justifies the investment. Neptune's mysteries touch fundamental questions about planetary formation, atmospheric dynamics, magnetic field generation, and the potential for life in ocean worlds. Solving these mysteries advances our understanding not just of one distant planet, but of planetary systems throughout the universe. Consider what we'd learn about planetary interiors. Precise measurements of Neptune's gravitational field would reveal how mass is distributed inside the planet, testing models of layered versus uniform composition. Does Neptune have distinct shells of different materials? Or does its interior mix gradually from the rocky core through ice-rich mantles to the gaseous atmosphere? Gravitational data combined with magnetic field measurements would constrain interior structure, revealing whether the immiscible layer model correctly explains the bizarre magnetic field. Atmospheric studies would revolutionize our understanding of weather on ice giants. Observing Neptune through complete seasonal cycles would show how atmospheric dynamics respond to changing solar heating, internal heat flow, and seasonal variations. Why does Neptune's atmosphere cool unexpectedly? Why do storms reverse course? How do winds reach supersonic speeds with minimal solar input? Long-term observations would answer these questions, revealing the fundamental physics governing ice giant atmospheres throughout the galaxy. The magnetic field deserves dedicated study. Neptune's field wobbles dramatically as the planet rotates because the field center is offset from the rotation axis. Mapping how this field varies with position and time would reveal where currents flow in Neptune's interior, testing theories about thin shell dynamos versus core convection. Understanding Neptune's magnetic field would illuminate a regime of planetary magnetism unlike anything seen elsewhere, with implications for how magnetic fields are generated in intermediate mass planets around other stars. Triton demands exploration. The Moon's active geology, thin atmosphere, and potential subsurface ocean make it one of the solar system's most intriguing bodies. Is there liquid water beneath Triton's ice shell? Does that ocean connect to the surface through geological activity? Could it harbor life, protected from space radiation by kilometers of ice while warmed by tidal heating? An orbiter could study Triton repeatedly, mapping surface composition, measuring ice shell thickness through radar sounding, and monitoring geysers to understand what drives them. The ring system needs investigation. Why do some arcs persist while others fade? How do shepherd moons maintain arc stability despite differential orbital motion that should disperse them? What processes create the dark ring material? Close observations would reveal ring particle composition, size distribution, and dynamics, testing theories about how rings evolve and interact with nearby moons. Other moons deserve attention. Neptune has 14 known moons, most discovered recently and barely studied. Proteus, Neptune's second largest moon, shows a heavily cratered surface, suggesting ancient geology. Nereid follows an extremely elongated orbit, possibly indicating capture from the Kuiper belt. Smaller, irregular moons might be captured asteroids or fragments from ancient collisions. Understanding Neptune's moon system would reveal the complex gravitational dynamics and collisional history of the outer solar system. Mission planning is underway. NASA's Jet Propulsion Laboratory has studied various Neptune mission architectures, evaluating different trajectories, payloads, and scientific objectives. European and Chinese space agencies have proposed their own ice giant missions. International collaboration might enable the mission too expensive for any single agency, combining resources and expertise to achieve shared scientific goals. Technology continues advancing. Ion propulsion systems could reduce travel time. Advanced power systems might generate more electricity from radioisotope sources. Improved autonomous navigation would allow spacecraft to adjust trajectories without Earth-based control. Better radiation-hardened electronics would survive the journey more reliably. Each year brings incremental improvements that make ambitious missions more feasible. Public interest supports exploration. Neptune captures imagination despite its distance. People want to know what secrets hide in that distant blue world, what forces drive its impossible storms, what mysteries lurk beneath its clouds. That curiosity translates into support for space exploration, encouraging funding agencies to prioritize missions that address fundamental questions about our solar system. The window is closing. Triton's orbital decay means the moon's geological activity might not persist indefinitely. Future generations might find a geologically dead world, its geysers extinct, its atmosphere collapsed. Studying Triton now captures a unique moment in solar system history when this captured Kuiper Belt object remains active enough to reveal its secrets. Neptune's formation history connects to exoplanet science. Understanding how Neptune formed and migrated inward helps interpret observations of Neptune-mass exoplanets orbiting other stars. Did those planets form in place or migrate? Do they have similar compositions and interior structures? Do they generate magnetic fields like Neptune's or follow different patterns? Answering these questions requires understanding our own ice giant thoroughly. The broader context matters. Neptune represents a class of planets that dominates galactic demographics. Every insight we gain about Neptune informs our understanding of thousands of exoplanets we'll never visit. Every mystery we solve about Neptune's weather, interior, or magnetic field helps interpret observations of distant worlds orbiting alien suns. Neptune stopped being just our solar system's 8th planet and became a key to understanding planetary diversity throughout the universe. Future telescopes will discover more Neptune-like exoplanets. The James Webb Space Telescope already studies exoplanet atmospheres, detecting molecules and measuring temperatures on worlds dozens of light years away. Future missions will push these capabilities further, characterizing atmospheres in increasing detail. But interpreting those observations requires understanding how ice giant atmospheres behave. What drives their weather? What chemical processes occur under different conditions? Neptune provides the ground truth for interpreting distant observations, so the case is clear. Neptune demands exploration, not just for its own sake, but for what it teaches us about planetary systems everywhere. The mysteries accumulating since Voyager 2's brief encounter call for resolution. The bizarre magnetic field, the diamond rain, the reversing storms, the persistent ring arcs, the erupting moon. Each mystery represents a question about fundamental physics that extends far beyond one distant planet. The journey won't be quick or easy. Engineers face formidable challenges, designing systems that survive the decade-long voyage and operate reliably in Neptune's harsh environment. Scientists must prioritize limited observations, choosing which questions to address first among dozens of compelling mysteries. Budget planners must justify the expense against competing priorities. But the scientific returns justify every challenge. Neptune reveals planetary processes operating in regimes we've barely explored. Its weather runs on internal heat rather than solar input. Its magnetic field emerges from thin conducting shells rather than deep core convection. Its interior might separate into immiscible layers like oil and water. Its largest moon erupts with nitrogen geysers, despite being one of the coldest objects in the solar system. Every aspect of the Neptunian system challenges our understanding and expands our knowledge of what's possible. That's why we need to go back. Not just to satisfy curiosity, though Neptune certainly deserves our curiosity. Not just to complete the catalogue of solar system planets, though that remains unfinished business. We need to return to Neptune because understanding this distant world illuminates planetary processes throughout the universe. Because the mysteries we uncovered decades ago still await resolution. Because Neptune's secrets might reveal how planets form, how atmospheres evolve, how magnetic fields are generated, and whether life can exist in ocean worlds far from the sun. The universe contains billions of Neptune-like planets. We've studied exactly one of them, for exactly one day, 37 years ago. Everything we've learned since then came from telescopes pointed across 4 billion kilometers of space, squinting to see details on a distant blue disk. That's not enough. The questions we've accumulated, the mysteries we've discovered, the fundamental physics we've glimpsed, all demand closer examination. Neptune calls us back across the solar system's edge, promising revelations about planetary science that ripple throughout our understanding of the cosmos. The journey is long, the challenges substantial, the wait frustrating, but the destination holds answers to questions we're only beginning to formulate, mysteries we've barely started to recognize, and insights that will reshape how we understand not just Neptune, but thousands of worlds throughout the galaxy that share its nature. Looking up at the night sky, you can't see Neptune without a telescope. It's too distant, too faint, lost in the cosmic darkness beyond Saturn. Most people live their entire lives without thinking about it. Just another planet in textbooks, another blue circle in diagrams, another entry in the catalogue of worlds orbiting our sun. But Neptune isn't just another planet. It's a warning written across 4 billion kilometers of space that the universe refuses to behave according to our comfortable assumptions. Every certainty we held about Neptune has crumbled under scrutiny. The iconic deep blue color, artificially enhanced. The simple ice giant composition, possibly more rock than ice. The stable atmospheric temperatures, wildly variable for reasons unknown. The predictable storm behavior, storms that reverse course and defy every model. Even the planet's discovery, astronomy's greatest mathematical triumph, succeeded despite calculations being fundamentally wrong about Neptune's mass. We've been wrong about almost everything. This isn't a failure of science. It's a revelation about the nature of reality itself. The universe operates according to principles far stranger than we imagined when we first pointed telescopes toward that distant blue speck. Neptune's mysteries aren't bugs in our understanding. They're features of a cosmos that delights in exceeding our expectations. Diamond rain falls through superheated ice. Magnetic fields wobble from offset centers. Storms rage at supersonic speeds, powered by internal furnaces. Ring arcs persist where orbital mechanics says they should dissipate. A moon erupts with nitrogen geysers at temperatures that should freeze all activity solid. Each discovery reveals physics operating in regimes we've barely explored, under conditions we can't recreate in laboratories, at scales that challenge our ability to observe or measure. And we've observed all this from 4 billion kilometers away, mostly based on a single spacecraft encounter that lasted less than a day, 37 years ago. Imagine what we've missed. What processes occur during Neptune's 40-year seasons that we've never witnessed? What transient phenomena appear and vanish between our infrequent observations? What subtle variations in magnetic field structure, atmospheric chemistry, or ring dynamics escape detection because we're watching from so impossibly far away? The exoplanet revolution transformed Neptune from solar system curiosity to galactic archetype. Telescopes discovered that Neptune-mass planets are among the most common worlds orbiting other stars. They're everywhere, more abundant than gas giants like Jupiter, more prevalent than rocky worlds like Earth. Understanding ice giants suddenly became crucial for interpreting observations of thousands of exoplanets we'll never visit. Every mystery about Neptune is really a question about planetary processes throughout the galaxy. How do intermediate mass planets form in protoplanetary disks? What determines whether they become ice-dominated or rock-dominated? Why do some develop bizarre, offset magnetic fields while others generate Earth-like dipoles? How do their atmospheres respond to different levels of stellar heating? What drives their weather when internal heat dominates over external energy input? Neptune holds answers to all these questions, but only if we go back. The technical challenges are real. Nuclear power requirements, decade-long travel times, autonomous operations across light-hour communication delays, multi-billion-dollar price tags competing with other scientific priorities. These aren't trivial obstacles. They're why Neptune remains the least explored planet in our solar system, despite being discovered in 1846. Yet those challenges grow less insurmountable each year. Power systems improve, propulsion becomes more efficient, autonomous navigation grows more sophisticated, international collaboration enables missions too expensive for single agencies. The technology that seemed impossible when Voyager 2 launched in 1977 is routine today. The technology that seems daunting now will be commonplace when a Neptune orbiter finally launches. The real question isn't whether we can go back. It's whether we choose to. Whether we decide that understanding ice giants matters enough to commit resources and time to the endeavor. Whether Neptune's mysteries deserve the same attention we've devoted to Mars, Jupiter, and Saturn. Triton adds urgency. The moon spirals inward, gradually losing orbital energy to tidal friction. Its geological activity might not persist indefinitely. The geysers erupting today could fall silent as tidal heating diminishes. The thin atmosphere might collapse as the moon's activity wanes. We're witnessing Triton during a geologically active phase that might not last. Future generations could find a dead world, its secrets frozen beneath ancient ice. More immediately, the scientific questions accumulate faster than we can answer them from Earth. Neptune's atmospheric temperature dropped 8 degrees over 15 years. Then the South Pole warmed 11 degrees in just 2 years. Why? Some ring arcs faded while others persisted. Why? A storm reversed course against all predictions. Why? Each observation generates more questions than answers because we're trying to understand a dynamic, evolving world through snapshots separated by months or years. The case for returning to Neptune isn't about satisfying curiosity, though Neptune certainly deserves our curiosity. It's not about completing the catalogue of solar system exploration, though that remains unfinished business. We need to go back because Neptune illuminates planetary processes operating throughout the universe. Because understanding ice giants transforms how we interpret exoplanet observations. Because the mysteries we discovered decades ago still await resolution, and new mysteries appear with every observation. Most fundamentally, we need to return because Neptune challenges everything we thought we knew about how planets work. It's a world that shouldn't be where it is, shouldn't generate the heat it produces, shouldn't drive weather as violent as it displays, shouldn't maintain magnetic fields as bizarre as it possesses. Every aspect of Neptune's existence contradicts comfortable assumptions about planetary physics. That's exactly why it matters. Science advances not by confirming what we already believe, but by discovering phenomena that force us to expand our understanding. Neptune is a masterclass in how the universe exceeds our theories, how nature operates according to principles we haven't yet grasped, how reality resists reduction to simple models. The next mission to Neptune won't just study one distant planet. It will revolutionize our understanding of how planets form, evolve, and behave under conditions far from their parent stars. It will test theories about planetary interiors, atmospheric dynamics, magnetic field generation, and orbital evolution. It will reveal whether Triton's subsurface ocean exists and potentially harbors life. It will answer questions we've carried for 37 years while raising new questions we haven't yet imagined. And somewhere beyond Neptune, in the darkness past Triton's orbit, the Kuiper Belt stretches outward toward interstellar space. Billions of icy objects orbit in that distant realm. Leftover building blocks from the solar system's formation, pristine samples of the material that built the planets. Triton came from there, captured billions of years ago when it wandered too close to Neptune's gravity. What other treasures wait in that frozen frontier? A Neptune orbiter could study Kuiper Belt objects during its journey or after completing its primary mission. It could observe these distant worlds up close, revealing their compositions and structures in ways impossible from Earth. It could transform our understanding of the solar system's outer edge while simultaneously revolutionizing ice giant science. The path forward requires vision, commitment, and patience. Engineers must design systems that survive the decade-long voyage. Scientists must prioritize observations among dozens of compelling mysteries. Funding agencies must commit resources despite competing priorities. The public must support exploration that won't return results for 15 or 20 years. But the destination justifies the journey. Neptune represents a class of planets dominating galactic demographics. Every insight gained there illuminates thousands of exoplanets orbiting distant stars. Every mystery solved advances our understanding of planetary processes throughout the universe. Neptune isn't just our solar system's 8th planet. It's a key to comprehending planetary diversity across the cosmos. The universe is vast, ancient, and filled with wonders that exceed our capacity to imagine. Neptune reminds us that even in our own solar system, even among planets we've known for nearly 2 centuries, mysteries persist that challenge our deepest understanding. It reminds us that the cosmos refuses to behave according to our comfortable assumptions, that nature operates according to principles far stranger than we've yet grasped. That's not a limitation of human knowledge,